Jack, what's the question?
Howdy. I was curious if you could tell us what UCST and LCST stood for.
No, I can't tell you.
Okay.
That's part of the quiz.
I understand.
All right, everybody, we got 2 more minutes. Then we're going to finish the quiz and begin today's lecture. Okay, for those of you already finished, you can pass down the other side of the aisle. All right. All right. All right. When you finish, pass down the aisle. Okay. So everybody, welcome back to another lecture. So we're almost finishing up everything in thermodynamics. There are a few items I want to discuss today to finish it up. Okay. So what we're going to do today is to first recapture what we discussed in the last lecture, to remind everybody about the importance of Flory-Hagen theory. That's actually part of the question too for you guys to understand the link between these two. Then we're going to discuss about what is the role of the chi has played in the Flory-Hagen theory and how you can actually predict the chi parameter even before you start them, and how you can measure them experimentally in some cases. Okay, so with that, we should finish up the textbook and what has been outlined there. In the lecture note, I indeed put a little bit extra curriculum. If you're interested to know some of the later development to the modification of Flory-Huggins theory to make it better, you're welcome to read them, and you're welcome to stop by my office to ask a question. So with that, we should finish the chapter 7 of the thermodynamics of the polymer. Okay, so if we have time, I will do a quick review of this class, the whole chapter of 7, before we finish today. Then next Tuesday, we will have some office hour for everybody. If you have questions how to study for the exam, we're going to go through all the homeworks on Thursday. Then we're going to have a test on Tuesday, a week and a half from now. Okay, so let's first take a look at what we have discussed. Spinodal point, those are crucial for you to decide what a phase diagram would look like. And at the end of the day, Flory-Huggins theory should be able to help you predict what is a phase diagram, if it will be a UCST behavior or LCST behaviors, or if you would have other interesting phase behavior. But it's all encoded here, and you should be able to get all these if you understand. So as everybody sees, the chi parameter plays a big role. So what is the role of the chi parameter? So that's the topic we're going to talk about today. These are some of the older lecture notes, but still valid here. So we're going to discuss a little bit how do we understand what is this chi parameter. Okay. If everybody recall, when we define the interaction parameter between two species, we talked about W11 is the interaction between the same molecular, W22 and W12 is interspecies. And that's how we define the Flory-Huggins parameter, right? And Z is its closest neighbor. So if you look at Wij, it's a generic term to describe what is the interaction you had between two species. We know that for any given interaction, it will depend on dipole-dipole interaction, which is inverse proportional to the distance, but its dependence what's each dipole moment for this given species. What is useful then, if we apply this very simple concept, this is Rij, means distance, power of 6, into how we define the chi parameter, we can reach a conclusion that when we apply W12 will be equals R12 square, alpha 1, alpha 2 will be equals to alpha 1, alpha 2, each to the cubic. Then you can reach the conclusion it will be minus average of W11 and W22. This has an important application, which here tells you we can rearrange the equation what we have above to get to these ZW will be equals to W11 root square, W22 root square, and then you take an overall square of it. If we actually define a cohesive energy density, which is written as mu I VAP, what this parameter is says, if you vaporize any liquid, how much energy you need to input to vaporize it. If you boil water, what happens when you heat the liquid up is you're splitting the intermolecular interaction. Okay, think about in the classroom, everybody is holding hands with each other. It's like liquid. There's short distance bonding interaction. And when you heat it up, it will become vapor. And these vapor water molecules are much farther away, so you're effectively breaking the bond energy. And how big is strong this bond energy depends on what molecule you're breaking, right? If you have some of the molecular are have stronger dipole interactions, they tend to take much higher energy to break them. So cohesive energy density is basically defined as number of Avogadro number, the nearest neighboring number, and Wi divided by 2. This parameter you can actually, between two solvents or two molecules, the chi will defined as average density for your material. This you can calculate. If you know the molecular weight, if you know the density, you can calculate what is this average volume. Divided by RT, R is Avogadro constant, T is temperature, multiplied by delta 1 minus delta 2 square. Okay? And these are solubility parameters you can look. So those terms are R and T. Once you define the temperature as a constant, so your chi parameter really depends on how big D1, D2, delta 1, delta 2 differs. So if you have two material, their solubility parameter are so far apart, you're going to have a very, very large chi. Because imagine if this value is 1, this is 10. 1 minus 10 will be equal to minus 9. Square will give it 81. But if this is a 1, this is 2, you're going to only have the chi to be value relative is about 1. So your chi is going to increase a lot if you have solubility parameter is very far away on the spectrum. This is actually a pretty good way to estimate what is the chi would be the chi parameter based on this solubility parameter. And I kind of explained to everybody, solubility parameter originate from the fact that you need to look at cohesive energy density. Okay? So how strong, how easy it is to vaporize and break the bond in a given molecule. So combining all together, if I given two new material, if they're already being measured before, I could go to either Polymer handbook, go to the page, look at, let's say, polystyrene versus a new, let's say, PET. You can look at a solubility parameter and use above equation to calculate what's the chi. You probably, if you're tasked to comparize them, or your manager is asked to choose a couple of material to make a new composite, that's how you can easily, before you start, to know if there's potentially going to be a problem in phase separation based on the chi. If their solubility parameter is close, then you can make them, likely to make them mix. Okay? If they are not mixed, then you probably need to think about comparizer or other approaches to make them comparize. It sounds solve all the problem, but in reality, what we measure is not exactly what we has predicted based on solubility parameter. One of the challenges is when you have new material that tend to be not measured, or you have the materials that might not be following this very simple empirical equation. So what can we do? One way is like when people measure so much material, you accumulate so many experience. The experience tells the user of this approach is we're typically offset. We underestimate this value. So commonly in real practice of this approach, we actually apply a constant at the end. So chi will be equal to what we have discussed before, plus a 0.34 value. Okay, as you can see, you raise the baseline for that. That tends to be raised what is the chi value would it be. And it has worked out better. For example, if we look at using the solubility parameter, we can reach that for delta 1, delta 2. This will be 0.06. So polystyrene and PMA are relatively compatible, but isoprene and dioxane is not. And these values are based on the top equation. If you want to calculate more carefully, they will be even higher. So in other words, entangled system, right? So it's not necessary with a phase separating to the side scale quickly. You can see by optical microscope, which typically can look at features up to microns, but not at the nanometer phase separation. So X-ray or neutron scattering are very powerful. In the early days, you can look at how much scattering signal, which is proportional to phase separation, to look at those phase diagram. Once you get the phase diagram, you can correct what the chi value is. There's a lot of good examples in early days how people look at phase behavior, phase mixtures. So I won't go into detail. But generally speaking, you can use measurement of phase diagram to back calculate what's the chi property. Okay, so we still have quite some time. So why don't we do a quick review of this class? So what we have learned in this chapter and how we prepare for this particular chapter. So let's go back to the journey where we started. If everybody recall, in the chapter 6, we're only looking at the chain conformation. In other words, if everybody recalls, what we did in September is to look at different molecular models that can predict how rigid your polymers are, how big the size of your polymer, how if the polymer is adopting an idealized chain or swollen chain or collapsed chain. It's all about size, dimension, etc., etc. So starting this chapter 7, we start to understand the thermodynamics. As I mentioned at the beginning of the lecture, we are talking about if the system will be likely taking a mixed phase or not. That's where we were hoping to achieve. And through this, most of the lecture in October, we discussed the two important things. So let me take a look through short note. So we discussed about all the thermodynamics of the polymer solution, right? When we started the lecture, we first talk about how to define the enthalpy and entropy in the mixing. And everybody should know this going into the test, right? So what is the role in entropy by x1 log x1 and plus x2 and log x2, right? So quite straightforward. What about enthalpy of mixing? We also discussed. Based on how molecular are contacting another molecule, we define the pair interaction parameter W11, W12, and we also talked about how you can define enthalpy of mixing, which will be equals to RT multiplied by x1, x2, and chi. x1, x2 are just how many numbers of those molecules, right? So combining these two, for about 2-3 lectures when we discussed all these concepts, we finally reached the delta G with respect to how entropy and enthalpy would work for a mixed system. From that, we went from regular theory, if everybody recall, to consider what is the molecular connectivity effect. So Flory-Hagen theory is based on regular lattice theory, and we basically evolved from a very of the mixing. Once we had this, we start to look at phase diagram. And for the next couple lectures, we discussed how we can get from how we should read the phase diagram in the first question, right? We discussed how you can have different UCST, LCST behavior, and where they could originally come from. We then discussed how you can link this Flory-Hagen series to the phase diagram and how you can draw a bridge between these two. It's not too hard as well. As long as you get delta G and chi value, you can predict a phase diagram based on the definition of spinodal point and binodal point, right? So once we know these, you should be able to construct a phase diagram pretty comfortably. given any structure, okay? You have to know what is definition of binodal curve, how we get there. What is definition of spinodal curve? Second derivative with delta G with respect to the x or the molar fraction is going to be equal to 0, define spinodal curve. And you need to know another concept is what is the critical point? What is critical temperature, okay? These, I hope everybody could answer those questions at the end of this second